Okay, my friends, so we've done a couple ranges now. We figured out that the average range contains about half the people. We know that the moderately above average range has about 7% of the people. What else we got? We got the below average range has about 16% of the people. Now, because of the symmetry of the curve, we also know, for example, that the above average range has to have 16% of the people too, right? Because 110 to 120 is the same position to the right of average as 80 to 90 is to the left. So it's got to capture the same amount of area. Similarly, moderately below average, 70 to 80, has to be 7%, just like moderately above average. Let's take a trip back to the spreadsheet and see how to do these less than and more than areas. All right, friends, let's do the below 70 IQ first. Now, calculating what the Z-score is for 70 isn't super challenging. You take 70 minus 100, which is negative 30, divide by 15, which gives you a negative 2. Just real careful when you're looking at this spreadsheet. If you don't, this one we don't have 2 Z-scores, we only have 1. If you only have 1, you only use the top one, Z1, and that'll make sense when you get over here. So I'm going to put in negative 2, and I want the area below that negative 2. And right there you can tell it's shading it for you. It's negative 2 and below. You see negative 3, negative 4. Technically it goes on forever. And it tells you the area is about 2%, which tells us that 2% of the population walking around have IQs that are rated as significantly below average. Again, I'm not trying to assign meanings to this. This is just what the scale tells us. Similarly, let's go with the IQ score of above 130. Now, 130 is on the other side of the average. 130 is 2 standard deviations above, so I'm going to change that 2 to a positive 2. Again, we're only using Z1 because we're only talking about one Z-score. And you want to shift this over to above. And you could have guessed that it was around 2% from our work before. As a matter of fact, some of you may have already started goofing around with this by putting in like, well, what if we had, negative 2 to 2? Is that the 95%? Oh yeah, it is. There's a 95%. And how about the 1 and the negative 1? Is that the 60? Oh, there's a 68%. How about the 3 and the negative 3? Yeah, there's the almost 100%. And some of you would say, wait a minute, it's not really 100%. There's actually, there it is, 99.73. Everything you learned from before still holds now. This tool just allows you to get that much more precision. Speaking of precision, let's go deeper than even this chart. Okay, friends, let's get away from IQ. I think we've kind of done everything we can with IQ, and it's not the most interesting data set. It's fun, and it lets us get into our spreadsheet and see how it works and understand Z-scores and things like that. And the spreadsheet is going to work for any bell-curved data, any normally distributed data. So as I was kind of looking around for the next one to look at, I found, I stumbled upon an old one that we chatted about, newborn baby weights, which is kind of fun. So I decided let's just use that one. So I was like, what could interest people in newborn babies? And I thought, oh, okay, so we could actually make up some problems based on like health characterizations. For example, we could ask, how do you define when a baby is underweight? So I went and looked, because I didn't know the answer to that, and I went and looked. And it looks like when a baby is below the 5th percentile, they're underweight. When a newborn is below the 5th percentile, they're underweight. So what does that mean, below the 5th percentile? Now we got to think back to percentiles, which we haven't talked about in a couple weeks. So let's take a look. Here's a bell curve. And I'm not going to use the baby numbers yet. I'm just going to use standard deviations because that applies to any bell curve. 0, that's average. If your newborn is average, exactly average, they are the 50th percentile because they are heavier than half of the babies out there. Boom! Underweight babies are going to be below average. And they're going to be located somewhere where they are only heavier than 5% of all newborns. Now, when you look at that, you might think to yourself, oh, I remember 5%. That's the opposite of 95%. We know the answer to this one. But be careful, though. Your 95% that you knew was 95% in the middle, not 95% above. And that's where the next part of the spreadsheet's going to come in handy. What we're going to do right now is we're going to do a two-step process. First thing we're going to do is we're going to figure out what Z-score right here, what Z-score cuts off 5% of newborn baby weights. And then we're going to convert that Z-score to an actual baby weight. Let's do it. Okay, friends, so where we're going to be now is the bottom part of the spreadsheet. Why the bottom part? Because now we're going to start with an area. We're looking for the 5th percentile, which means we're looking for a Z-score that chops the bottom 5% of the area off of the top 95% of the area. So the dividing line between the lightest 5% and the heaviest 95%. Now, if we have the area, which we do, we're going to put that down here in the area as a decimal box. Boom! And if you take a look at that, it's already set up. The button is clicked for area left. We now know the Z-score is negative 1.645. That tells us that in order for a newborn to be in the bottom 5%, they have to have a weight that is at least 1.645 standard deviations down from average. But what's that baby's weight? Well, let's figure it out. We now know that the Z-score is negative 1.645. So we're 1.645 standard deviations down from average. We need to know a couple things before we go any further. The first thing we need to know is what is the actual in pounds newborn baby weight? And that's from before. We know that the average is going to be 7.5 pounds. And the standard deviation is going to be 1.3 pounds. I say is going to be. This is just from years of data collection. So we can, and we did this before in previous videos, the 7.5 is going to go right here on average. Because the average is 0, Z-scores. So how far down is this one? Well, it's going to be less than 7.5. So what you might be thinking is, well, we can undo what we did before. So before, we had a raw score and we're able to convert it to a Z-score through that formula. Z equals X minus mu over sigma. And this is the conversion. If you have a raw score, you've already got these two numbers. You're going to know that already from whatever you're studying. Whether it's baby weights, IQs, pregnancy lengths, tree diameters, whatever. You're going to know these two numbers. You're either going to know the raw score or the Z-score. In the previous examples, we knew the raw score. Here, we know the Z-score. So here's what I vote we do. Let's do a little tiny bit of algebra. I'm going to clear the board here for a sec. Let's do a little tiny bit of algebra and figure out how to switch in this formula where the Z is with where the X is. And then we'll see if we can make some sense of that. Let's do it. Ah, the magic of cinema. Now, if you don't like algebra, just suffer through this for like 45 seconds and we'll be done. We have to undo everything that's happening on this side. So if you think about the order things happened on this side, if we start with the raw score, the first thing that happened was we subtracted the average. The last thing was divide by the standard deviation. Think of this as like taking apart your carburetor on your weed whacker, which if you had me in Math 105, we actually did that in a video. To get it undone, we have to do those operations in reverse order. So since the last thing we did was divide by the standard deviation, the first thing we have to do is multiply by the standard deviation. So we're going to take that standard deviation and multiply it by the Z-score. That should make total sense because it's the Z-score tells you how many standard deviations you're going, and that's the value of one standard deviation. That numerically makes sense to me. Now we got to deal with this. Going back to this, the first thing we did was subtract the average. We now have to add the average. So if we take the average plus the number of standard deviations times little sigma, that's going to give us the raw score. Okay, so I think we're good. All we got to do now is run some numbers. We know that the average baby weight is 7.5 pounds. 7.5 pounds. Plus the Z-score. Now the Z-score is negative 1.645. Oops. times the value of the standard deviation, which was 1.3 pounds. And if you think I can do that in my head, I come up with a baby weight of about 5.4 pounds. So any baby that's around 5 pounds, 5 ounces or lighter is going to be termed underweight. So that would be the number that goes under this 1.645, that about 5.4 pounds. It's not negative because babies can't have negative weight. The Z-score is negative because it's below average. But when we convert that into something meaningful, which we're going to have to do, we do have to do that. It's going to end up taking on the context of the problem. You might notice pounds came in when we started talking about the weights. Let's look at another one. Let's look at heavy babies. All right, friends, so I did a little Googling about overweight newborns, and as you might imagine, there's no consensus, as there often isn't with things like this. Even underweight at 5% probably isn't medically consensused. But the number that I find interesting is I popped up with an 8%. So the heaviest 8% of newborns are the ones that are considered overweight, which is so interesting. So now there's two ways you can actually do that with the tool we're using right here. Okay, first of all, you got to put the 8% in as a decimal if you want to use the 8%, 0.08. Now, you now need the area right, don't you? Those are the babies that you need to find the weights of. 1.405 standard deviations above average. But some of you may have also realized something. Wait a minute, if 8% are above, that means 92% are below the 92nd percentile. And notice it's the exact same Z-score. Exactly the same Z-score. It doesn't matter if you go 92% below or 8% above. The same Z-score does that cutting. We could have also used this idea previously with the 5%, right? 5% below is the same as 95% above. They leave you at the exact same Z-score. So anyway, you got some choices there, which is nice. And you'll get used to that as you goof with this chart more. All right, so now we've got to convert a Z-score of 1.405 to actual baby weight. So I recommend we use our handy dandy little converter formula, which means take the average of 7.5 pounds, add it to the Z-score, 1.405, times the value of the standard deviation of 1.3, and we come up with a baby weight of about 9.3 pounds, which I love as I love that. I didn't know what the number was going to be. I was 9 pounds, maybe a little bit over as an infant. My sister was 10. So both of us were pushing the definition of an overweight newborn. Oh, I love that. All right, next video, we'll do a recap of everything we've done so far and look at one more data set.